Okay, good morning. Welcome to our webinar. My name is Craig Prater. I am the CTO of Photothermal Spectroscopy Corp. You may have seen my colleague's name, Owen Dillon, as the original presenter. Unfortunately, Owen's got a bad case of strep throat, so I hope I'll do as a substitute this morning. What we're going to talk about today is a new technique called O-PTIR, and I'll explain what that means a little bit later. And this is a real breakthrough in the field of infrared spectroscopy. So those of you who are familiar with infrared spectroscopy, use it in your work and your research. We hope that you'll see that we address some of the major limitations of conventional FTIR microscopy and add some real benefits. So here's an outline of our presentation today. First of all, I'm going to give you a little introduction to our new company, Photothermal Spectroscopy Corp, and then talk a little bit about the background of infrared spectroscopy and spatially resolved infrared spectroscopy or infrared microscopy. And then I'll introduce this new product called Mirage, which is an IR microscope using this technology, this O-PTIR technology that I'll talk about. Then I'm going to hand it over to my colleague, Kurt Marcott, who's a senior partner at Light Solutions and a real expert in the field of infrared spectroscopy, infrared microscopy, and he'll talk about applications of this technology. And then at the end, we'll take your questions. So a little background on Photothermal Spectroscopy Corp. So we come out of a company called Anisys Instruments that many of you may be familiar with. Earlier this year, Anisys Instruments split up into two divisions. This new division, Photothermal Spectroscopy Corp, was founded to take forward this technology, this O-PTIR technology, that is the core of our Mirage IR microscope that we'll talk about today. The remainder of Anisys Instruments was recently sold to Bruker Nano, the leading company in the field of atomic force microscopy, and a leader also in infrared spectroscopy. And so our Nano IR product line, or the Nano IR product line, and other related products that were developed originally by Anisys are now being sold by Bruker, and Photothermal Spectroscopy Corp, which was founded by the management team of the original Anisys Instruments, is now working on this Mirage photothermal IR microscope. So a little background into infrared spectroscopy for those who may not be familiar or need a refresher. The basic idea is that we have infrared light that we have incident on a sample surface. And if we have the frequency of that infrared light tuned to a molecular vibration frequency, then a portion of that light gets absorbed by the molecules and causes the molecules to vibrate, for example, stretching in this animation. If conversely, the frequency of the infrared light does not equal any of the molecular vibration modes, then the infrared light simply passes through the molecules unabsorbed. So if we make a measurement then of the absorption of infrared light versus the frequency of the light, we get a series of peaks, and each of these peaks corresponds to a specific molecular vibration where that IR light was absorbed, and this pattern of peaks acts as a fingerprint that you can use to characterize, or in many cases uniquely identify, the chemical species in a sample. And in the mid-1990s, this IR spectroscopy was combined with high-resolution microscopes and infrared detectors and array detectors to provide spatially resolved infrared spectroscopy, which then led to spatially resolved chemical analysis. And this field has really taken off. these IR microscopes are very widely used in a large number of application areas. I've highlighted a few of them here: polymers, life sciences, forensics, etc. But these are all areas where these microscopes are used to look at the chemical heterogeneity of samples to see, for example, the distribution of different chemical species, and then to go into individual locations and use those spectra to chemically characterize and analyze the samples. As powerful as IR spectroscopy has been, there are a number of limitations, a number of common problems, and this slide highlights a few of them. First of all, the spatial resolution, I'll talk more about this in a moment, is limited for IR microscopy by the longer wavelengths of infrared light versus what we use in white light microscopy. This is showing a comparison, for example, of images on a test standard, one test standard imaged in visible light, another test standard, a similar one imaged in infrared light. And you can see in the visible light image, you can resolve these line pairs, the very fine line pairs, but when you do the same thing in infrared, the fine line pairs get blurry, and I'll talk more about the limitation of that in a moment. The other issues that are common with infrared spectroscopy is that sample preparation can be complex, especially for doing measurements in transmission, where it's necessary to prepare a thin section that's thin enough to let the infrared light penetrate through the sample. Or alternatively, one can use ATR, which can avoid some of the sample preparation issues, but then it's a contact technique where you have to push an ATR crystal into the sample surface with a controlled force to be able to get good spectra and good images. And then there's a problem, especially in reflection-based FTIR, where you can have dispersive artifacts, where the spectra get distorted due to dispersion effects and scatter effects, so that the peaks don't appear as they would in traditional transmission FTIR. Now, the key limitation that we wanted to focus on was the spatial resolution limit of conventional IR, and there is a fundamental limit in conventional optical microscopy called the diffraction limit, and described by this gentleman, Ernst Abbe, that says that the smallest that you can focus light, that waste here, is going to be set by the wavelength of light and the index of refraction, and then the cone angle here of the light. Well, there's limitations, there's practical limitations to how big you can make that cone angle, and the fact that we're using infrared light with wavelengths 10 times or more bigger than visible light means that we can't focus that spot to as small as we would like, and that's what leads to the fuzziness in these images that you see here. So that optical diffraction has been a fundamental limit of infrared microspectroscopy. So to overcome this, we developed this instrument called the Mirage IR microscope, and it can achieve sub-micron spatial resolution using this O-PTIR technique that I'll describe in a little bit. And here are just a few of the big advantages. First of all, and I'll show you examples of each of these, but the Mirage microscope can achieve transmission quality FTIR, excuse me, it can achieve spectra that are the same quality as FTIR spectra in transmission, but not in transmission, but in reflection mode. So it doesn't require the thin sectioning that conventional FTIR does. It's also a completely non-contact technique, so there's no ATR crystal that you have to push into the sample. And then the spatial resolution, in this diffraction equation, you can see that the resolution depends on the wavelength. So when you go out to longer wavelengths, the spatial resolution gets worse. Well, in this O-PTIR technique, the spatial resolution is independent of the IR wavelength. You get a constant spatial resolution throughout the wavelength range. And I just want to, this little graphic here is trying to give you a sense of where this Mirage and this O-PTIR technique is on the spatial resolution scale. So on the one hand, you have instruments like conventional FTIR based microscopes, or those using ATR that could be in the 5 to 10 micron spatial resolution range, and again, depending on the wavelength. And then Ansys Instruments, the company that we were with before, developed this instrument called the Nano IR using an AFM-based photothermal technique, and that can achieve spatial resolution down to the 10 nanometer length scale. And I mentioned that this instrument now being sold by Bruker. The Mirage technique or the Mirage product that we're talking about today is really in a sweet spot between these two. So it's about 10 to 20 times better than conventional FTIR, though obviously coarser than the AFM-based technique. So how does this O-PTIR technique work? Well, we start out with an infrared microscope objective, and we have a sample down here, and the sample has some heterogeneity. So let's imagine that these blue regions are going to absorb infrared light in the wavelength range that we're going to use. Now, if we were to try to measure this with conventional infrared microscopy, we would focus our light to a spot that could be much bigger than these features of interest. You know, again, limited by that IR diffraction limit, that AB diffraction limit. Well, if we were to image it, however, with visible light, we could focus that visible light to about 10 to 20 times smaller than the infrared light. But we want to make do a chemical analysis here using infrared. So how can we use these two ideas together? Well, the idea is if we bring in pulses of infrared light and we tune that infrared light to a wavelength that corresponds to an absorption band of, for example, these blue regions, then that infrared light is going to be absorbed and cause these regions to heat up. And as they heat up, we'll have thermal expansion and other photothermal distortions that we can then probe with this visible light beam. And what happens is that we see a change in the angles and intensity of the light that is reflected off of the sample. So by capturing that visible probe light with this microscope objective, we can measure that photothermal distortion with this visible probe beam. You know, this is just putting it all together in one slide. We have the IR beam focused on the sample. IR light causes the absorbing regions to heat up and thermally expand, causing this photothermal distortion in the sample. And then we're using that visible light beam to probe that photothermal distortion. Now, where does the big advantage come from? It comes from the fact that we can get high spatial resolution from this visible light beam that we can focus to a very small spot. And the size of the visible light beam is independent of the wavelength of the infrared. So we can sweep this infrared wavelength to measure the absorption spectra, but the spatial resolution of the visible probe, it remains constant. So this is just a summary of some of the key benefits of this O-PTIR technique. We can do point spectra and line arrays where we're taking you know, just seconds per spectra. We can do hyperspectral arrays where we are taking full spectra at an array of points on a sample, typically around 1 second per spectrum. Kurt will show some examples of this. And then one big advantage that we have over traditional FTIR microscopes is that our infrared laser source, instead of being a thermal source, it is a tunable infrared laser. And so we can tune to any individual absorption band and then collect high resolution images at those fixed absorption bands, those fixed wave numbers, and we'll show you examples of that. And then additionally, we can readily export our spectra into external IR materials databases that you can use just as you would for traditional FTIR spectra for characterization and identification of unknown materials. So let me show you some data to back up some of the things that I said. So I mentioned that we can get transmission quality spectra in reflection mode. So these are measurements on 3 different polymer samples. These were films, no special sample preparation. We just focused the IR and visible light on the sample surface and measured them in a reflection configuration. And you can see here in, I can't even tell without looking closely which is which. I think it's the, maybe the red is the library spectrum and the blue is the spectra from the Mirage. And you can see for each of these, we got matches to library spectra greater than 98%. You know, this is again done with no special sample preparation, no thin sectioning, et cetera. And these spectra, by the way, they were exported into or imported into this know-it-all database by Biorad. And then we did blind searches to find the best fit. So you can see that we matched to those materials databases. I'm about to hand this over to Kurt to talk about some applications. We only have time today to talk about a handful of applications in the polymeric materials and defect analysis and a little bit of bio. But I just wanted to make the point that wherever FTIR microscopy is currently used, we believe that this Mirage instrument can make the same measurement with the benefit that it can achieve both higher spatial resolution, less sample prep, and without the need to use contact. So with that, I'm going to turn it over to Kurt Marcott, who will overview some specific applications.
Thanks, Greg. So I'm going to talk a little bit about some polymer systems. One area where this technique is working extremely well is multi-layer film characterization. You can do really nice identification of multi-layer films, and also for identifying contaminants and defects. So the first example I want to talk about is a multi-layer packaging film. And this particular sample is actually a 300 nanometer thick section. And you can see from the visible image that there's about 7 layers in that sample. So when we mounted this in the Mirage instrument, we collected a series of 93 spectra spaced by 500 nanometers along a line across each of those layers. And so over a total of 46 microns, you can see each of those 93 spectra overlaid, and you can see the kind of signals and noise we can get in just a minute of measurement time. This is an experiment you'd never be able to do with FTIR because you could never get spatial resolution down to half a micron. You could get the spectra, but not nearly at that spatial resolution. Just to demonstrate that we do achieve 500 nanometer spatial resolution, on the next slide, we pick out 2 spectra that are right next to each other in this multi-layer film. So these 2 spectra are only 500 nanometers apart, and you can see that Mirage is easily able to provide the distinguish between these 2 layers, which means it has a better chance of identifying important tie layers in multi-layer film samples. So if you're already using FTIR microspectroscopy to identify layers in multi-layer films, you'll be able to do the same thing with Mirage, and you'll be able to do it at much higher spatial resolution. On the next slide, we show, I think, an even more significant advantage of the Mirage capability. The image that I'm showing here is from the block section that the previous 300 nanometer thick section was cut from. So the top part of the visible image is actually a clamp that's holding the epoxy embedded film inside of the clamp. And we're literally looking at the edge of the film, and it's not a thin section at all. So the colored dots on the visible image correspond to the individual spectra shown on the right-hand side. And these are collected using that reflection-like geometry. So even though the sample is thick, we're getting nice looking spectra that resemble IR transmission spectra. We don't see any scattering artifacts. And this is another big advantage of the Mirage technique. A lot of times you're not able to cut a thin section. In this case, you don't need to. You can still do chemical identification of all of the layers in the multi-layer film on a thick sample. The next slide, I'm looking again at this this time the thin cross section, and you can see that we've again got some spectra of the individual layers in the film. And on the right hand side, you see the fingerprint region spectra that I showed before. But if we use a different laser that works in the high wave number range, we can also get information about the CH, OH, and NH stretching bands, which is extremely important. One of the layers in the film, in fact, we were able to determine was actually a carboxylic acid, not just EVA, because we were able to see that in the high wave number range. So a lot of times having the high wave number range can give you additional information to solve problems. So you can see the really high signal to noise we can get out of the instrument. Going back to the block sample on the next slide, I want to point out, as Craig mentioned first, that we can do single wave number imaging, something that's not possible with FTIR. With FTIR, you get the whole spectrum whether you want it or not. Because we're using a tunable IR laser, we can, for example, take the laser, tune it to 1742 and collect an image and light up the layers in the sample where the ethylene vinyl acetate's absorbing strongly. If we switch the laser wave number to 1545 reciprocal centimeters, we can light up the polyamide layers of the film. And similarly, in the high wave number range, we can get the NH stretch from the polyamides and the CH stretches from the polyethylene layers in the sample. And these are collected much quicker than a full hyperspectral data set. On the next slide, we go back to the block sample, and now we collect a hyperspectral data cube over an area of about 20 by 80 microns of the sample, spanning all the layers of the film. So in this case, we spent 1 second per spectra, and so in about an hour, we're able to collect a complete hyperspectral data cube. So just like if I was using a focal plane array detector, I get a data cube where each pixel in the image represents a full spectrum, and each slice at a single wave number gives us a infrared spectra. So you can see in the image there's a line of spectra collected along the full length of all the layers in the film. All of those spectra are overlaid on the right hand side, and you can see the signal to noise ratio of the spectra we get in a 1 second data collection. And if we just grab the band at 1740 and want to display it, so if we just highlight that band, we can light up the layers of the sample in red where there's a strong absorbance at 1740 reciprocal centimeters. If we switch now on the next slide and tune to the wave number at 1546, that's an amide 2 band. And now if we image, see where that's absorbing strongly, you can see all the polyamide layers in the film. And if we switch one more time to 1470, we can light up where the long chain CH2 scissoring band is showing up strongly in the film. So we have a full hyperspectral data cube. We have the ability to collect 1 spectrum a second and do hyperspectral imaging. We can also sit at a single wave number and get higher resolution images faster, or we can sit at a single point and get very high quality infrared spectra. All of this, I think, better than what you can do with current FTIR, and without having to contact the sample and without having to cut a thin section. So on the next slide, I show an example of a defect identification in a polymer film. This film happens to be polypropylene, and you can see in the visible image right in the center there, there's kind of a defect. And if you look at that, you can't really tell from a visible image what it is. And I think one of the things that makes the way we looked at this with Mirage Unique is this sample was actually 215 microns thick. So you would never be able to do a transmission measurement with FTIR through this. You'd probably have to do ATR, but we were able to do this reflection-like measurement. And so what we did is we collected a series of spectra in the matrix region in red that are spaced by 2 microns. And then we collected another series of spectra in blue that are in the defect region. And if you look at those, basically, they're both polypropylene spectra. But if you look closely, you can see that some of the crystalline bands, for example, the one that's highlighted with the star at 998 reciprocal centimeters, that's a crystalline band of isotactic polypropylene. That's appearing very uniformly at all locations in the red area of the sample, but in the blue area of the sample, it's sometimes there and sometimes not there. So what this result is telling us is that that defect is not a foreign contaminant. It in fact is isotactic polypropylene, but it's not got a uniform crystallinity. It's got variable crystallinity. So it represents an area of the sample where the crystallinity was not uniform. So that's one way you can help to identify a sample, and without preparing a lot of sample preparation or contacting the sample. On the next slide, we show another real example of a hole that was drilled in a material. It's maybe about a 50 micron diameter hole. And on the left-hand side of the image, you can see the focus is set to be aligned with the top surface of the sample. But what happened was there was some sort of a residual material, actually 20 microns below the top surface of the sample. And if we move the focus down 20 microns, we can light up this foreign material. This would be impossible to get a spectrum of by any normal FTIR technique I know of, even ATR. You could never get an ATR probe down into that hole. But with Mirage, since we're not touching the sample, we can probe down below 20 microns into the sample, the top surface of the sample, collect the spectrum, and then do a library search versus the know-it-all database. And you can see that this particular contaminant is a really nice match with calcium stearate, with the library spectrum in red and the Mirage spectrum in black. Finally, just want to talk a little bit about biological samples. We'll be having future webinars. I think we'll do more about this. But one of the problems with biological samples is you have to measure them on a substrate that maybe your pathologist doesn't want to give it to you on. Pathologists would love to give you a sample on a glass microscope slide, because that's always what they use. But in this work we did with Professor Nancy Pleshko's group at Temple University, she typically cuts bone sections and puts them on barium fluoride substrates because you're able to transmit light through. So this is data she collected at Temple University on a PerkinElmer spotlight. You can see the visible image on the lower left, and above that is an IR image with the taking out the data from the absorbance at 1030 reciprocal centimeters. So in red, covering this area of the sample that's 6 millimeters by 7 millimeters, all the areas that light up strongly red in that image are where there's a lot of bone and a large amount of absorption. So there's a whole lot of spectra there. Each one of them represents a 25 micron by 25 micron area of the sample. On the next slide, we showed that same PerkinElmer spotlight data in the upper left. Nancy sent us the sample, and we ran the Mirage spectrum from an area where she said there was a large concentration of bone. And what we did is a hyperspectral data cube. We collected an array of 50 by 50 spectra that covers an area that's 25 micron by 25 micron. So basically, we have 2,500 spectra in the same area that the PerkinElmer spotlight produced one spectrum. And it took us about 45 minutes to collect this data set at 1 second of spectrum. And you can see if we look at the slice at 1047 reciprocal centimeters, we're lighting up areas of the sample where there's a strong absorption due to the mineral content of the sample. And if we switch to the slice at 1660, we're lighting up where the protein matrix is absorbing strongly. And if we pull out a single pixel spectrum, and that's the unsmooth spectrum, you can see that's the quality of data that we get. in a single 1 second scan. So we can do hyperspectral imaging on this slide. For those of you who might be attending the SPECS conference next week in Glasgow, I'll have some even more data where I demonstrate that we don't even have to cut thin sections. We can actually look at PMMA blocks of bone tissue without sectioning them at all and do similar kinds of work. And I think this is going to be really important to the bio community to be able to get data with a minimal sample preparation. If you're going to try to get clinical people to accept IR spectroscopy, they're going to not want to do sample prep if they don't have to. I guess in summary, Mirage is a new photothermal-based non-contact optical microscope that does not require thin samples. It achieves wavelength independent sub-micron IR spatial resolution. The spatial resolution depends on the visible probe laser. It doesn't matter about the IR. And it produces IR spectra in a reflection mode that match transmission spectra that you get from commercial FTIR database searches. So at this point, I'll pass it back to Craig, and I think we'll have time for some questions.
So there's a question: is the O-PTIR technology something unique? You know, is there any other maker model that uses the O-PTIR technology? So yes, the O-PTIR technology is exclusive to Photothermal Spectroscopy Corp. There are a number of academic research groups that have been working in this area, and we've had the pleasure of collaborating with them, and we've secured exclusive licenses to this technology. So we're the only supplier of the O-PTIR technology right now. Then there's a question about what's the speed and resolution of the wavelength scan. So we use a couple of tunable infrared laser sources. One that goes from about 800 to 1900 wave numbers, and the other one that goes from about 2700 to 3600 wave numbers. The one that does the 900 to about 800 to 1900, we typically will do a spectrum in about a second. You know, so we're doing about 1,000 wave numbers per second, and it has a spectral resolution of less than 1 wave number. And then the other source is a bit slower. It's more on the many seconds to a minute per wavelength sweep, and the spectral resolution is also a little bit coarser. But we're happy to talk with folks about their specific applications and what source or sources would work best for their application. Let's see, there's a question about when we have a sample that reflects the probing visible light diffusely, how can we measure the thermal response of the sample? So maybe Kurt, can you talk about some of the samples that you've measured and how rough they are and whether we can still measure them with the visible light probe?
Yes, we're able to measure samples with surface roughness. It has an autofocus capability. As you move from one point to the next, you can get the laser to be, the visible laser to be in focus with the top surface. So you can get spectra of pretty rough samples. The ultimate rough sample was the one I showed at the end where there was a defect 20 microns deep inside of a hole, and we were able to tune the focus down into the hole and get the spectrum. So as long as you get most of the samples scatter the visible light, and it's not been a problem to get spectra.
Thanks, Kurt. There is a question about the differing materials will respond thermally in different ways. How are these correlated in the data collection? So that's true that the photothermal response of a sample will depend on both the IR absorption coefficient, but also its thermal properties. For example, its thermal expansion coefficient, or how much the index of refraction changes with temperature. And so if you are comparing, looking at just a single wavelength image, it may be hard to discriminate whether your contrast is coming from IR absorption differences or the thermal property difference. So what we typically recommend is taking multiple images at different wavelengths, because when you change to different wavelengths, you can then create a ratio image that will normalize out for all of the differences in the thermal properties, such that you're just seeing the differences in the IR properties. And that same thing is true when we do a spectrum, is that when we're doing a spectrum, the only thing we're sweeping is the wavelength. So all of the thermal properties remain constant, and so the features that you see in the spectra are due exclusively to the changes in IR absorption in the sample. Let's see. There's a question about how does the visible probe measure the thermal expansion? What happens is we're more broadly measuring a photothermal response of the sample. So there can be effects from thermal expansion. There can be effects from a change in index of refraction of the sample with temperature. And what we are doing is we're measuring the change in the intensity of the probe light beam. So we're collecting that probe light beam with the objective. We're measuring that change in intensity as a function of the position on the sample, or as a function of the wavelength of the infrared light as we're sweeping the infrared light. So how can it achieve high spatial resolution? It can achieve high spatial resolution because we can focus that visible probe beam to a much smaller spot than we can the infrared light. And the reason is that the visible probe beam has a wavelength that's 10 to 20 times shorter than the IR light. So when you go through that calculation of the Abbe diffraction limit, you can get a much smaller number for the IR. There was a question, Kurt, for multi-layer film measurement, is cross-sectioning required?
No, it isn't. We demonstrated that we can get off a stub sample that a section was cut from. You can also look at the cross section, but it's not necessary to cut a thin cross section to be able to make a measurement.
Yeah. So Kurt showed examples of measurements first on a cross section, and then we followed that up with measurements on a what he called a block face sample, which is just where you've cut or polished the top surface, but it's still a bulk film. Let's see. There is a question about what is the advantage of O-PTIR over nano-IR? So from our perspective, these techniques are very complementary, or can be very complementary. So what the nano-IR excels at is achieving very high spatial resolution, down to the level of 10 nanometers. The disadvantage of the nano-IR, of course, is that it involves an atomic force microscope and so requires a bit higher level of skill to operate. The advantage of the O-PTIR is it's optical microscope based only, and so the learning curve is much quicker for the O-PTIR. The spatial resolution is obviously not as good as the nano-IR, but we have a lot of interest, in fact, in combined tools where you can use the O-PTIR for still getting 10 to 20 times better spatial resolution than conventional FTIR, and it's very fast for covering large areas, getting point spectra. And then if there are regions that you want to study with higher spatial resolution, you can make the measurements on the nano-IR. So we're continuing to work with our partners at Bruker to support that combination. There's a couple of questions on cost, and we'll contact you offline to discuss the cost, because there's details of configuration and laser sources, et cetera, that come into play. There's a question, Kurt, about is it possible to apply this technique to a particle, say a few tens of microns in diameter?
Yes. A lot of times you can simply take your particle and put it on a piece of double sticky back tape, focus on the top part of the particle, and get a spectrum of it without getting the spectrum of the tape. That would be one way to do a sample like that. Pretty easy sample prep, and you get a nice spectrum of a 10 micron particle.
Let's see, there's a question about would it be possible to go to far IR range? And the answer is in principle yes. If suitable longer wavelength IR sources are available. So the O-PTIR technique doesn't really care what the wavelength is of the source. It just cares that it's creating an absorption in the sample that causes a photothermal distortion, and then we can certainly use the the visible probe beam to measure that absorption. Let's see, there is a question about using shorter wavelength light to increase spatial resolution, and yes, that's certainly possible to use different wavelength probe sources for either spatial resolution or for other reasons. There's a question about what is the size thickness limitation for the sample. The standard Mirage sample holder holds a 1 by 3 inch glass slide, and we can accommodate samples, I think, up to about 15 millimeters thick. But these are things that we have some flexibility on, because the sample stage itself is much bigger than that. It's around I don't know, 4 by 4 inches, 3 by 4 inches of travel, and so talk to us if you have a larger sample requirements. There's a question about is there a sample holder that allows conditioning of the sample under specific gases? That's something that we don't have right at the moment, but we are interested. So feel free to talk to us about specific needs and applications that could help guide that effort in the future. Let's see, it says, can graphics of single wavelength monitoring be done within the standard software versus exporting data? So within our standard software, we have the ability to capture point spectra, capture single wavelength images like Kurt talked about, and do these, collect these hyperspectral data arrays. And within our software, we have some set of analysis functions for the spectra and for creating single wavelength images from hyperspectral data arrays, or spectra from average spectra from a region of the sample. But we do additionally support exporting the data to third-party software packages. For example, we can export individual spectra as a CSV file that you can import into any analysis software. We do direct exports into a couple of third-party packages that we'd be happy to talk to you about. And then there's a question that says, basically this is IR that can do mapping in the micrometer range, and the answer is yes. So this is basically an IR microscope that in many ways is similar to the operation of a conventional FTIR microscope, but it overcomes the spatial resolution limit, so that we're down in the the micron or even 500 nanometer spatial resolution range. Okay, it says, there's a question that says, how much surface roughness can the technique tolerate for one image? You know, for example, with the calcium stearate in the hole, you showed you needed to change the focus to see the material at the bottom. So we have an autofocus capability that you can turn on to adjust the focus every X number of spectra. And so you can accommodate more surface roughness, but you pay a price in terms of the image acquisition time. So if you set it up to do lots of autofocuses, especially if you have a lot of corrugation in the sample, then the measurement time will go longer, you know, based on the number of times you have to do the autofocus. So it is advantageous to have a smoother sample if that's something that you can prepare, but we do have ways of dealing with rougher samples as well. There's a question about the wavelength of the visible probe beam. Right now we're using 532 nanometers, though I mentioned we have some flexibility in that, so if you have a desire for another wavelength, you can let us know. There's a question about, is the sample compartment an open system, and if so, is it possible to couple with other in situ measurement techniques? So the measurement compartment is enclosed for a couple of reasons. It's enclosed for one, so that we can purge the sample environment to keep the air dry, reducing the impact of water vapor absorption bands. And then also because we're using a relatively powerful visible laser beam, we have the compartment closed for laser safety reasons. But we'd be happy to talk to you if you have a custom application in mind, if there's a way that we can support that. There's a question about do you have to use only thick samples or can it be a thin film? Yeah, Kurt, can you talk about, you know, so of course it does not have to be a thick sample. We've done many thin samples. Kurt, can you comment on, you know, some of the thinnest samples that we've done?
Well, the one example I did show was 300 nanometers thick, and the signal to noise on that was extremely good. I've seen decent data down to 100 nanometers thick. And if the sample's thinner, the spatial resolution will also be a little bit better if you can cut a thin section, because you won't be sampling, you know, deeper into the sample. But certainly 100 nanometer thick sample can be done.
Okay. Let's see, there's questions about, have any tests been done in the lateral resolution of the microscope? Yes, we have done measurements of that. You know, Kurt showed an example of two spectra that were 500 nanometers apart and showed you know, dramatically different spectra. We've also done measurements on you know, resolution test samples. Okay, there's a question that says, how do you obtain wave number, wavelength dependence? Is it Fourier transform principle, or do you use a diffraction grid? So this question is describing techniques that are used by conventional or older infrared spectrometers. So this is an important point. Let me spend a little bit of time on that. So a conventional Fourier transform infrared spectrometer, or FTIR, uses a broadband light source. So it basically has a hot filament that is emitting a whole spectrum of different infrared wavelengths all at once. So you illuminate all of the sample with a whole bunch of wavelengths at once, and then you have to use a Fourier transform principle to be able to, or an interferometer to be able to get out the wave number dependence. We do not do that. So what we have instead is we have tunable infrared lasers. So we can tune them to single wavelengths, and we are then measuring the IR absorption at that single wavelength. And then to get a spectrum, what we do is we sweep the wavelength of that infrared laser while we're measuring the photothermal response with the the visible probe beam. So the reason that this is a really big advantage, Kurt touched on this, is that, for example, right here, these are images that Kurt showed where we got these images without acquiring full spectra. What we did is we simply tuned the laser to some of these individual absorption bands. So we would tune, for example, to this carbonyl band, and then quickly get a single wavelength absorption image. So you can do a handful of IR absorption images in a tiny fraction of the time that would take for a full hyperspectral cube by either FTIR or the Mirage instrument. Let's see, there's a question about can accessories such as a heat stage used in FTIR and Raman be used in the Mirage? So we would be very interested to talk to you more about your applications. We've certainly gotten some requests for heating and cooling stages, and that is in our roadmap to provide that. It's not available right at the moment, but we will have it in the future. And so if you'd like to influence the target specifications for those accessories, we'd be really interested to talk to you. So Kurt, there was a question about on the bone measurements. Were the spectra acquired on a glass slide or another substrate? And then maybe can you mention whether or mention again the requirements or lack of requirements for a specific substrate?
Yeah, the sample we looked at of the bone was exactly the same sample that was the FTIR data was collected on. So it was on a barium fluoride window, but it didn't need to be for the Mirage measurement because we measured it in reflection. I have another example we didn't show in this webinar where we looked at stem cells that were on silicon wafers. And in that case, the Temple group had measured transmission spectra on the silicon wafers, and they got a lot of band distortions because of the high refractive index of the substrate. When we ran them with Mirage, we saw no distortions at all. The spectra looked like transmission spectra. We've also looked at samples on low-E glass slides. These are microscope slides that have a thin coating of metal and reflect the light. So a lot of people who study biological samples by IR use those slides and do double pass transmission. Sometimes they produce some dispersive artifacts. We can run off those slides as well, and we don't get any dispersive artifacts because we're measuring the photothermal response and a reflection measurement. In fact, it could be on a glass slide, and we would get doesn't matter what the substrate is from Mirage. You can put it on a barium fluoride, you can put it on a silicon wafer, you can put it on a glass microscope slide. That Mirage spectra will always be the same. You can't say that about FTIR.
Thanks, Kurt. There's a question asking if we can compare this work to the early work of Fournier and Baccara in like the late 70s and early 80s, where they coined the term Mirage effect. So the O-PTIR technique certainly descends from the history of this early photothermal work and other photothermal work. My memory of how the Fournier setup worked was that and I may be incorrect here, but my memory is that they shined a light beam above the sample, and they were measuring distortions due to the change in index of refraction of the air above a heated sample. So what's a bit different about what we do is that we are focusing our probe light beam directly onto the sample, and we are not so sensitive to the changes in the index of refraction of the air, which is quite small, but instead we're measuring the photothermal response of the sample itself, so its thermal expansion and the change in index of the sample itself. And this is part of the reason why we get very high spatial resolution. If we were measuring an effect from the air, basically, the heat would go up into the air and diffuse, and we wouldn't get high spatial resolution. Instead, we're measuring it right at the point of absorption. There's a question about, does the sample need to be transparent or clear? Otherwise the visible light could be absorbed. Can the technique still work? And so certainly samples that are clear present the least challenge for this technique. They're very easy to do. Samples that are not transparent, we have certainly measured many samples that are not transparent, samples that are diffusive samples, some samples that are colored, but the issue tends to be if it's strongly absorbing and in the visible light wavelength that we use, we have to use lower probe beam power to avoid damaging the sample. And so there will be an impact on the amount of measurement time required to get a spectrum or an image. There's a question about can we make sample measurements? So for customers who are interested in evaluating the technique for purchase, for example, if you want to see about getting funding and want to have justification or check out the viability of the instrument for solving your problems, we are absolutely willing to do complementary sample measurements, so feel free to talk to us about that. There is a question about, can you measure visually transparent samples like glass? So yeah, there's no problem measuring on a sample that's visually transparent because we get a sufficient reflection of the probe beam. Even on something transparent like glass, you're going to get about 4% of the incident light reflected off of that surface back towards our detector, and so that's plenty of light for us to do the analysis. And that's an application that we've done, looking, for example, at defects on glass. There is a question about their interference from water vapor and CO2. So I mentioned previously, and let me go into a little bit more detail. The system is sealed and purgeable. We supply it with an optional air dryer, or if you have nitrogen at your facility, you can plug that in and purge it. There's a humidity sensor built into the system so that you can see that low humidity is being maintained. And so when we do purge the system and maintain it at low humidity, we see minimal effects from water vapor and CO2. Let's see. Oh, there's also a question about is there a liquid nitrogen cooled detector? So we do not have a liquid nitrogen cooled detector. So we don't have, in fact, a traditional IR detector, because remember, we are measuring the infrared absorption with the visible probe beam. So we're using a visible photodiode that does not require cooling to operate. So that's another advantage over conventional FTIR, is that you don't need liquid nitrogen to achieve high signal to noise. There's a question about inorganic materials. Can you do inorganic materials? And the answer is yes. If the inorganic materials have IR absorption bands within the range of the tuning range of our lasers. We have done some work on, for example, mineral samples and like meteorite samples. Okay, I think we have run over time at this point. If you want to contact us, our website is www.photothermal.com. And with that, I'll thank you very, very much for your participation, your many great questions, and we look forward to talking with you in the future. Thank you so much.